In this video, I want to examine some word problems that we've seen before, the types we've seen before, just as a review, and also to go over linear equation solving and maybe even systems of equations problems. So linear applications are a good way to sort of summarize past work. So and also review. So let's take a look at this first problem here. So in the outback in Australia, Betty and Carl go camel riding in the same direction along the same path. Betty's camel travels at 6 miles per hour. Carl's camel travels at a little slower. 3 hours later, they are 2.4 miles apart. So you can sort of visualize this, right? So they take off from the same place and they travel for 3 hours. And this is where Carl is at that moment, and this is where Betty is at that moment. So we'll call Carl C and B there, and this distance here is 2.4 miles. Now, this is one of those things where things are moving, so we're going to use the distance, rate, time idea, and for those problems we usually did by setting up a table. So, and along the rows we'll put Betty and Carl, and then we'll write the information we know about each of these and see if we can set up an equation. Now, when you set up a table, if you really label the table carefully, you don't have to use let statements. The table will speak for itself. So distance, rate, time. So what do we know? Betty's camel travels at 6 miles per hour. So that's 6. That's the speed at which Betty's camel travels, while Carl's camel travels at a slower pace. We don't know that. After 3 hours, they're 2.4 miles apart. Okay, so they both have been traveling for 3 hours. So we can put 3 at each of those. And we know they're 2.4 miles apart, so be careful. We don't get to put 2.4 miles anywhere here because 2.4 is not Betty's distance, 2.4 is not Carl's distance. However, we can find Betty's distance. It's going to be 3 times 6, so that's 18. And we can write something for Carl, except we don't know his rate, so we'll call it x. So Carl's distance is 3x. So now we need to come up with an equation. We do know that after 3 hours they're 2.4 miles apart. So this 3x represents Carl's distance, this one here, and the 18 represents Betty's distance right there. And if you take that difference, you end up with 2.4. So that is your equation. So you could have said 18 minus 3x is 2.4. Another equation that you could have come up with is to say 3x plus 2.4 is equal to 18. Either of those works. It doesn't really matter how, it just kind of depends on how you visualize it. I'm going to go with this first one. So I'm going to subtract an 18 from both sides. And that's going to give me 3x is equal to 2.4 minus 18. So 2.4 minus 18, and that gives me 15.6. And then I'm going to negative. And then I'm going to divide by negative 3, and I get 5.2. So that tells me that Carl's, so we can go back to answer the question, what is x? X is Carl's rate, so Carl's camel travels at 5.2 miles per hour. That was our first distance, rate, time problem in this series. By the way, there are many word problems here which I will do, but I'll break them up as we go along. So the next distance, rate, time problem is this one. It says 2 Coast Guard cutters are 225 miles apart, traveling towards each other, one from the east and one from the west. So again, let's draw a picture. So this is west, this is east, and they're traveling towards each other like so. And they're searching for a disabled boat. The eastbound cutter travels at 5 miles per hour faster than the westbound cutter. Okay, so the eastbound cutter, that means this one, this is eastbound, and this is westbound. right? Heading towards, that's what it means. So the eastbound cutter travels at 5 miles per hour faster than the westbound. If the two cutters pass each other after 3 hours, determine the average speed of each cutter. Alright, so we can set this up again with a table. So we'll say eastbound, westbound, distance, speed or rate, time. Okay, they're 225 miles apart. So the 225 is not something I can put into any of these distances, because 225 refers to the total distance they're apart, not each individual distance. I'm going to hold that off, putting that number in my table. The eastbound cutter travels at 5 miles an hour faster. So the eastbound one is 5 miles faster than the westbound. So whatever I have here, this is going to be plus 5. So if I let this be x, then this is going to be x plus 5 because it's 5 miles an hour faster. Cutters pass each other after 3 hours. So both cutters are traveling for 3 hours. Now, at this point, I can write down what the distance is, because the distance is going to be 3 times x plus 5, and over here, it's going to be 3 times x. And now that 225 comes into play, because when they meet, somewhere in between, each one has gone part way of that 225. So the distance traveled by the eastbound one added to the distance traveled by the westbound one is equal to 225. Let me erase this smudge and write it nicely. And so now this is a simple linear equation. We can solve by combining like terms. Six x minus a 15 on both sides, and I get 6x is equal to 210, then divide by 6, and I get x equals, so 210 divided by 6, 35. So we can report our answers back. So we can say the westbound cutter travels at 35 miles an hour, and the eastbound cutter travels at 5 miles an hour more, so 40 miles per hour. Let's look at another distance rate time problem. Laura drives along the interstate highway at 70 miles per hour until she encounters heavy traffic, slows to 50 miles per hour. The time she drove at 70 miles is 1 hour more than the time she drove at 50. The distance she drove is 70 miles per hour is greater than the distance she drove at 50. If the difference in the distances is 100, determine the time she spends at each speed. Okay, so the two parts of a trip we can think of as going along the road. So the 70 mile per hour part and the 50 miles per hour part. And so distance she traveled at each one's, rate's pretty easy, and then time. So 70 miles goes at 70 miles per hour part rate. 50 miles goes at 50 miles an hour part rate. At 70 miles she drove 1 hour more than at 50, so this is plus 1 more than this one. So if I let this one be x, I can let that one be x plus 1, and if I have those, I can fill up the distance part. So this is going to be 50x, and this is going to be 70x plus 1. Now if the difference in the distance she drove at the two speeds is 100. So they tell us that the distance at 70 is greater than, and the reason they tell us that is so you put that in front when you're finding this difference. So the difference at the distance of the two speeds is supposed to be 100 miles. So now we can distribute 70x plus 70 minus 50x, and so that's 20x plus 70 equals 100. So minus a 70, 20x is equal to 30, divide by 20, and x is equal to 3/2 or 1.5. We're talking time here, so it makes sense to we are much more familiar with saying r1/2 than 3/2. So 1.5 hours. So let's answer the question. She traveled 1.5 hours at 50 miles per hour, and she traveled 2.5 hours at 70 miles per hour. And how do I know this? Because it's 1 hour more than the 50 mile an hour part. Okay, next we'll look at some interest rate problems in the next video.